everyone, Katrina here, and today I'm going to tell you about compound angle identities and how to derive them. Be sure to subscribe for more videos like these. Okay, so compound angle identities are very important in trigonometry because they help us simplify problems as well as solve tricky trigonometric expressions and equations. They also aid us in performing trigonometric proofs. So today I'm going to start by showing you a few of these identities, and then we're going to use these identities to help derive some subsequent ones. Okay, let's dive in with the first one. So compound angle identities are when we have two angles that are either added or subtracted within the bracket of our trigonometric function. So basically we can divide our theta or decompose our theta into two other thetas, into two other angles. So here, for example, let's say we have sine A plus B. So we've taken our theta, so let's say A plus B is our theta, and we said that now that theta equals to A plus B. So instead of having a more complicated angle, we're going to actually take this out and essentially decompose it into some other more simplified versions of this. So sine A plus B equals to cos A multiplied by sine B plus sine A multiplied by cos B. So now let's go ahead and use this identity to help us prove the next one. So the next one is going to be sine of A minus B. So how can we use this first identity to help us with the second? Well, it's actually pretty simple. We can rewrite this as sine of A plus negative B, so that our second angle here, our B here, is now negative B. So let's take a look at that. So as a result, we now have, following our identity here, we are taking sine of A plus negative B, and this equals to cos A, right? So cos A sine B, so our B is now negative, so negative B, and then plus sine A, and then cos of B, and in this case our B is negative again. Okay, so this is where we're going to have to use our knowledge of equivalent trigonometric expressions, which I explained in my earlier video. So what this tells us is, from equivalent trig expressions, we know that sine of a negative angle is equivalent to negative sine of the positive of the angle. So sine negative B equals to negative sine B. In cos, if we have cos of a negative angle, that is equal simply just to cos of the positive angle. So in this case, it would just be cos B. We know this because sine is an odd function and it's periodic, and cos is an even function and it's also periodic. For further explanation, be sure to check out that previous video. So now let's go ahead and just simplify this so that we can derive the full identity. So that means we now have negative, we're going to bring the negative to the front. So negative, let's move over here a little bit. So we got negative cos A sine B, and then we simply just have plus sine A cos B, and now let's rewrite it so that the negative is in the center. So we've got sine A cos B minus cos A sine B. And there you have it. We've just derived the trig compound identity for sine of A minus B. So that's pretty neat how you can use the knowledge of one to help derive another. So now we have two so far. So let's go ahead and label those. So we've got our first one here for sine of A plus B, and then we got our second one right over there for sine A minus B. But what about cosine? We want to figure out those compound angle identities as well. So we're going to do a similar process. So we're going to start with cos of A plus B. And I'm going to give this one to you, and we're going to derive the negative one. So this equals to cos A cos B minus sine A sine B. And now, what about cos of A minus B? What is this equal to? So we're going to do that same process where we now have cos of A plus negative B and rewrite it in that way. So cos of A plus negative B, following our identity here, is going to be cos A cos negative B minus sine A sine negative B. And again, using our understanding of equivalent trig expressions, we know that cos of negative B simply equals to cos B, and sine of negative B is equivalent to negative sine of positive B. Okay, so let's go ahead and simplify this. So we've got cos of A minus B. That equals to cos A cos B. And then now we're going to bring this negative over here to the front. But then we have negative negative. We have minus negative sine A, sine A sine B. Okay, but what happens when we have this double negative here? You can use the little trick that the enemy of your enemy is your friend. So this is actually a plus. So therefore, we've derived now that cos of A minus B equals to cos A cos B plus sine A sine B. Very good. Now let's go ahead and use an example of why this could be important and how we can use it in practice. So our example today is we have cos of pi over 12. And we want to find an exact solution to this problem. Oops. There we go. So we want our exact solution. And what does it mean when we have exact solutions? I mentioned this a few times, but exact solution, that's hinting that you need to use a special triangle. And I have a few videos on special triangles, so be sure to check those out. But just to let you know, we have our two special triangles. We've got one that has pi over 4, and that's our 1 root 2 triangle. These are both right angle triangles. And then our second one is, if we've got pi over 6, is across from 1, and then across from pi over 3, we have root 3, and the hypotenuse or radius is 2. So this first one, 1 root 2, is our isosceles triangle, and then our second one here is our scalene triangle. So that means that we are looking for like the following angles. We either want some pi over 4, some pi over 3, and some pi over 6, because we know that we can create special triangles with these angles. But what about pi over 12? We don't have any special triangles where we can use that directly. So this is a great time where you can try to use or think of a compound angle identity that can help you solve this. So think about it this way. We have cos. So we either, our two candidates are some cos A plus B or some cos A minus B. So can we decompose pi over 12 into two angles, which are special triangle angles, and then apply this compound angle identity? So let's start by using a little cheat sheet on the side, and we're going to put these three angles, our special triangle angles, with the common denominator of 12. So we can see if we can add or subtract them to get to pi over 12. So let's just do that little exercise to help us visualize this. So pi over 3 is equivalent to 4 pi over 12. I'm just multiplying the numerator and denominator by 4. And then we have that, make some more space there. Pi over 6 is equivalent to 2 pi over 12. And lastly, we have that pi over 4 is equivalent to 3 pi over 12. So can you think of any of these that we can add or subtract to get pi over 12? Well, we can do pi over 4 minus pi over 3, right? We can do 4 pi over 12 minus 3 pi over 12, and that will give us pi over 12. So that essentially means that we've got our pi over 3 minus pi over 4. And those are two special triangle angles, which is amazing. So that means we can use them to find exact solutions. So let's go ahead then and utilize this compound trig identity right over here. So what will that look like for us? that means we now have cos of pi over 3 minus pi over 4. And following our identity, we have that this equals to cos A, cos B, so cos pi over 3, cos pi over 4, plus sine A, sine B, so plus sine pi over 3, sine pi over 4. And just to repeat once more so everyone's on the same page, our angle A is equal to pi over 3, and our angle B is our pi over 4, and we're using the cos A minus B compound angle identity. So now we basically just have these 4 terms that have a single simplified angle, which are also special triangle angle, that we can use directly to solve this problem. So let's go ahead and go through the steps of solving these individually using our unit circle. So let's go ahead with our unit circle here. We're going to say that we just need to figure this out. So we've got our cast rule. So we have CAST. Let's draw out our angles. So our domain, so we're going from 0 to pi over 2 to pi to 3 pi over 2 back to 2 pi. Okay, so our first angle here, let's start with pi over 3. So we know that's found in our quadrant number 1. This angle here is pi over 3. So from our, I'll just write that a bit better, pi over 3. So from our trig ratios, we know that cos is adjacent over hypotenuse, or x over r. And we also see here from our special triangle, we can fill it out, that opposite from pi over 3 is root 3, opposite from pi over 6 is 1, and then our radius is 2. Okay, and then let's fill that out. So we said that cos pi over 3 equals to our x value over our r value, according to SOHCAHTOA, which equals to 1 over 2. And now let's look at our sine pi over 3. So sine pi over 3 is equal to opposite over hypotenuse, or y value over radius. And in this case, that is equal to root 3 over 2. Okay, so now we have our unit circle for pi over 3. Let's just adjust this, and let's make this for pi over 4. So let's do that instead. So now we've got our pi over 4 triangle here, and let's fill out our special triangles. So we know that's our 1, 1, root 2 triangle, and let's find our trig ratios for each of those. So cos of pi over 4 equals to x over r, which is 1 over root 2, and then sine pi over 4 is our y over r, which is also 1 over root 2. So now we have a solution for each of these trig ratios individually. So all we have to do as a final step is put it all together. So that means that cos of pi over, so actually let's do our original one. So we're looking for cos pi over 12, which we rewrote as cos pi over 3 minus pi over 4. This now equals to cos pi over 3, this one here, which is 1 over 2, multiplied by cos pi over 4 over here, which is 1 over root 2, and then plus sine pi over 3, which is root 3 over 2, multiplied by sine pi over 4, which is 1 over root 2. So if we go ahead, we can then simplify this problem, and it equals to 1 over 2 root 2 plus root 3 over 2 root 2, which if you want, we can write this as what do we have here? 1 plus root 3 over 2 root 2. And that's your final answer. You have the option to rationalize this if you want, meaning to get rid of the square root on the bottom. And if you were to do that, then your final answer would be root 2 plus root 6 over 4. So in that case, you'd just be multiplying the numerator and denominator by your 2 root 2. And there you go. or actually you would just be multiplying, your numerator and your denominator by root 2 to get that. And so this was a great example to show you how we would use a compound trig identity in action to be able to find the exact solution to a problem using special triangles. So it allows us to essentially decompose this angle into two angles that we have special triangles for, and then we solve each of them individually and then put them back together. So be sure to write these down and remember them and think of them when you're trying to solve more complicated problems, and also be mindful for them when you're trying to prove trigonometric identities. And with that, I will let you go and keep studying. I hope everything is going well. Please be sure to subscribe for more videos and drop a like if you enjoyed this one. I'll see you next time.